Alright students, so in this video we're going to continue looking at linear combination of atomic orbitals, and we're going to think a little bit about the math behind it. And really here we're going to be giving some names to some types of integrals that will always appear when we do linear combination of atomic orbitals to create our molecular orbitals. So as a general rule of thumb, we won't do this math by hand, but you should have a conceptual understanding of how some of it works. So we're not going to go into too terribly much detail here, but you should hear and see some familiar terms as, to the Huckel Molecular Orbital Lab that you did this week. So we'll go back to our favorite simple molecule, the smallest, simplest molecule of H2+. And we already defined that we have two wave functions. We have the wave function for the bonding orbital where they add together, and the anti-bonding orbital will be the one that they subtract. So right now, for the purpose of this video, we're only going to deal with the bonding orbital. We could have chosen either one, so either the summation of the two wave functions on A and B or the subtraction, but we're going to choose the summation today. We can define our complex conjugate simply by applying the complex conjugate to both of the psi1s functions in our sum. So here we have psi1s star on A plus psi1s star on B, and they both are multiplied by their respective weight functions C1 and C2. And if we think about variational theory, according to variational theory, our average energy, remember, is the wave function, complex conjugate, Hamiltonian acting on the original wave function, all integrated, divided by the integral over all space of psi star psi. And here, we're going to be dealing with the bonding orbital, so MO plus is how I've denoted that. And this will be then the energy of the bonding molecular orbital if we were to do these integrals and take the ratio. So let's call the denominator, which is just psi star psi integral, as integral number 1, and the psi star Hamiltonian psi integral as integral 2, which we find in the numerator. So we'll start with the denominator, psi star psi of MO plus, and right now I've removed the integral. We'll put it back in a minute, but for now let's just write out all the possible terms because we have a binomial, right? We have C1 psi1sa plus C2 psi1sb for our wave function. So when we multiply that by C1 psi1sa star plus C2 psi1sb star, we're going to get 4 terms. So one of those terms will be C1 squared psi1sa star psi1sa. Then we're going to get a mixed term, C1 C2 psi1sa star psi1sb. We'll get another mixed term, but flipping the a and the b. And then we'll get C2 squared psi1sb star psi1sb. We can put back in our integrals here. Really, these are triple integrals in space, but I'm just denoting them as d tau with a single integral to denote that we are integrating over all possible space. And here, we have some familiar integrals, hopefully familiar integrals. All of these integrals that appear are known as overlap integrals, or denoted S, usually ij, which I and j would then represent the nuclei. This is just like in the Huckel Molecular Orbital Lab. And so really we can rewrite these terms as C1 squared SAA, the overlap integral on A, on only A, plus 2 times C1 C2, the overlap integral for AB, or SAB, plus C2 squared, overlap integral on B, or SBB. So some things we know are that the hydrogen-like wave functions centered on a single nucleus are normalized. We already proven this to ourselves, which means that SAA and SBB are both equal to 1. How about SAB? So this is going to depend on R. This is where we vary a little bit from Huckel Molecular Orbital Theory. So Huckel Molecular Orbital Theory said that this integral is 0, and that's because we're dealing with pi orbitals, which are very, very, very sensitive to R. But SAB, this if we're dealing with a sigma orbital, which often we are, is going to depend largely on how close the two nuclei are to one another. So you could think about you'll have more orbital overlap between the two 1s functions if the r is very small, or if the nuclei are very close to one another, and you'll have no overlap if they're far apart. And so let's deal with our second integral. Now this is the one with the Hamiltonian. Again, we're going to get 4 terms. The first only deals with nucleus A. So we have C1 squared, Psi1s A star, Hamiltonian acting on Psi1s A. Now remember, this is our full Hamiltonian, right? Whatever that looks like, this is our full Hamiltonian. And then we'll get 2 mixed terms, where in the first one the Hamiltonian acts on Psi1s B, and in the second one the Hamiltonian acts on Psi1s A. Forgot a star there, sorry. And then we have our last term, which is C2 squared Psi1s B star, Hamiltonian acting on Psi1s B. So we can get these terms. If we look at the first term and the last term, they look a little bit familiar, right? So let's put our integration in. The first and the last 2 terms look deceptively like just the energy of a 1s orbital on A or a 1s orbital on B. And these are often called our Coulomb integrals. And they're often denoted in a variety of ways. Your book is going to denote them, I believe, with the letter J. But in Huckel molecular orbital, we often denote them differently. So we're just going to call them Coulomb integrals and not denote them as anything in this video. The reality is, though, these aren't just pure energies, the first and the fourth term on A and B. Because really, they have this little something extra, right? Because your Hamiltonian has more terms than it would for just a hydrogen atom, right? It's also got these 2 additional potential energy terms which will be affected, and some kinetic energy terms. But if we look at the 2 terms in the middle, these are known as exchange or resonance integrals. These also showed up in our Huckel molecular orbital theory, and exchange or resonance integrals have different wave functions. So the Hamiltonian acts on one wave function, and the complex conjugate is of another wave function. So these are often known as exchange or resonance integrals. We can think of them as the energy associated with the electron being shared or exchanged by 2 different nuclei. So what are the resulting molecular orbital energies? We could do all of these integrals. We're not going to. We're not ever going to for this class. But we should understand how they're set up and where they come from. So what are the resulting molecular orbital energies if we were to calculate these or ask a computer to calculate these? So we can plot these, and we're going to come back to this plot later in Friday's videos. I'm going to plot energy versus internuclear distance, capital R. Remember that that's the internuclear distance, the distance between A and B. So for reference, we'll plot the energy level for a hydrogen 1s electron with a gray dashed line. The purple line is the E+. So this is the energy we would have just worked out with all the math above, or the energy of the bonding molecular orbital, the energy of adding the 2 wave functions. And you'll notice we have some interesting features. You may be thinking to yourself, this looks a little bit like a Morse potential. It does. So over here on the left side, at low internuclear distance, or really small internuclear distance, we can see that we have a huge increase in energy. The energy goes up towards infinity very quickly, and this is due to nuclear repulsion. But if we were to keep going at large R, we'd see that the energy will level off, and it will form an asymptote with E1s. And this represents dissociation from being a molecule, an H2 molecule, or in this case an H2+, to being an H+ atom, or 2 H+ atoms. And so we'll see dissociation at large R. And this, because the energy goes down, right, this is the bonding. We saw pictorially in the last video that this is bonding. This is a positive or constructive interference. So this is our bonding orbital, and our bonding is always going to decrease our energy or stabilize. So we're always going to get a lower energy for a molecular orbital than we would for 2 individual atomic orbitals. Now if we were to do all the math above, for the anti-bonding orbital, or when we subtract the two wave functions to get destructive interference, we'd see the blue curve for the resulting energy. So this is always going to give us a higher energy than it would for a single electron in a hydrogen atom. But you'll notice that at large R, it also converges to E1s, which remember is just that atomic hydrogen energy. And that's going to also be due to dissociation. So both the bonding and the anti-bonding energies will dissociate or converge to the atomic energy at large R. So some general statements about linear combination of atomic orbitals. For larger molecules, you would basically do the same thing, but the wave functions that you're combining are going to be your capital size, your multi-electron atomic orbitals from your Slater determinant. So it's going to get out of control very quickly. And another thing to note is no matter what kind of wave function you're dealing with, for every two atomic orbitals that you combine, you'll produce one bonding molecular orbital and one anti-bonding molecular orbital. Alright, so in the videos for Friday, we'll be continuing to explore molecular orbital theory. Much of this will be graphical and visual, so prepare yourself to be using some WebML.